Hi there, this is Lucy LeFramboise from ENG Suite, and today we are going to talk about our first normality test, the Anderson-Darling test. So in the next couple of weeks, probably more than a month or two, we're going to go through each of the tests for normality found in QE Suite. We're going to go through the math, when to use them, why to use them, and then after we've learned about them all, we're going to kind of compare them a little bit and see why certain ones may be more applicable in other scenarios. We'll touch on all of that in this video today on the Anderson-Darling test. All right, let's get started. So the Anderson-Darling goodness of fit test is a commonly used test in engineering because it's not just for the normal distribution. The Anderson-Darling test is a goodness of fit test, and like most goodness of fit tests, it's a hypothesis test. For the Anderson-Darling test, the null hypothesis is that the data follow the specified distribution. The alternative hypothesis is that the data do not follow the specified distribution. So, you'll notice it's specified distribution and specified distribution, not the normal distribution. We'll get into that later, but that's really because the Anderson-Darling test can be used for multiple distributions. Okay, but how does it work? Well, the Anderson-Darling goodness of fit test calculates a weighted comparison of the probability of each measurement's z-score to determine the discrepancy of the actual measurements and expected values from the distribution. So that is a lot of words there, and what it's really saying is that it's a weighted comparison of how likely each z-score is when you compare it to the expected z-scores. And by weighted, we just mean that different z-scores in different locations get a higher priority when it comes to calculating the Anderson-Darling test statistic. So for the Anderson-Darling test statistic, you'll find that it's usually the first normality test because it puts a higher weight on the tails, which means that if you have heavier tails, it's going to affect whether you pass and can assume normality or not. So it's going to be a little bit more selective than other tests. That's not what today's video is about. Today's video is really about the math behind it. But in order to understand the math, we have to understand what we're trying to do. So once we have these weighted values, we sum them and scale them using the number of samples to calculate our Anderson-Darling test statistic. Then, once we have the Anderson-Darling test statistic, we'll use a set of piecewise functions to calculate the p-value from that test statistic. And generally, we use the p-value and compare it against a critical value to determine whether or not we can assume the data follow whatever distribution it is. So when do we use the Anderson-Darling test? Well, in most organizations, it's going to be the first test that we use to evaluate normality. And that's really because it's more selective due to more weight being placed on the tails. And in engineering, we always like to start with the most selective and slowly open up our specifications. That way, we are erring on the safe side, right? In engineering, nothing is exact. Everything is about getting the best results with the current available resources. So if we stay in the smallest, most confined area, such as the most selective test, we know that we're in a safer place. We can never guarantee something, but we know that we're in a safer place. So that means that it can reject the null hypothesis, which is that the data follow the specified distribution, when other tests would fail to reject it, like the Ryan-Joyner, Jarkbara, Kolmogorov-Smirnov, and other tests. So if it rejects the null hypothesis, we can say that we can't assume that it follows the specified distribution. But maybe other less selective tests, like the Ryan-Joyner, which is just for normality, by the way, might say, yeah, we're good. We'll assume normality. Like I said, we always want to err on the safe side as engineers. So it's really just best to start with most selective. We kind of talked about that. These are really all the same point, just minor aspects of it. So the Anderson-Darling test can also be used to evaluate the goodness of fit with other distributions. So if you've ever done maximum likelihood estimation, individual distribution identification in Minitab or QE Suite, that individual distribution identification is actually using the Anderson-Darling test to evaluate which of those distributions your data fit the best. So to do this, the parameters for the other distributions must be estimated. And this is generally through maximum likelihood. If you use QE Suite, there's an excellent function, the maximum likelihood function, that actually estimates and returns those so you can see the values. We'll talk about that at a later date. It's really not that important right now. Minitab uses the exact same process for estimating those parameters as well. So the Anderson-Darling test is often used to determine the distribution that the data best fits. That's that individual distribution identification. Again, it's a selective test, and the fact that we use it for lots of distributions makes it a great pick when we're doing normality. Just because of its broad support, we like to use things that can be used in a multitude of scenarios, right? Okay, so interpreting the results. The Anderson-Darling test statistics. So this is that first value we calculate. What we know about that is that higher values correspond to lower probability that the data originated from the specified distribution. So higher AD test statistic corresponds to a lower p-value. All right, awesome. So then what's the p-value? Well, generally, we use a critical value to evaluate this p-value, and we use that critical value to determine if we fail to reject the null hypothesis or if we do reject the null hypothesis. In most cases, that p-value is going to be a 0.05. So if you know anything about p-values, you'll be great in this. As engineers, we tend to have a tough time with p-values because we think of them as pass or fail. Where if you're above 0.05, it's a pass. If you're below, it's a fail. We really don't like to use that, especially when talking in statistics. That can work in a scenario. We can say, oh, we failed for normality because our p-value was less than 0.05. But just remember that if you're above the critical value, then we fail to reject the null hypothesis. Okay? Above the critical, fail to reject. If we are below, we do reject. So I'm going to step away from statistics and talk like an engineer for a second. 0.05, not 0.05. If we're greater than our p-value, then we accept. Now, you can't say this, but as an engineer, I'm going to talk to engineers here. If we're above our critical, then we can assume and accept the null hypothesis. That is not a statistical statement. That is an engineering statement. We can accept that it's most likely true, okay? So we can go along with the null hypothesis. If it's below the critical, then we go along with the alternative hypothesis. Again, that is not a statistician statement. That is an engineer's statement, okay? Above critical value, null hypothesis. Below, alternative. Again, not a statistician statement. That's an engineer's statement. Okay, so let's do an example here. We have a p-value of 0.08 and a critical value of 0.05. Our p-value is greater than or equal to the critical value, so we fail to reject the null hypothesis. In this case, the null hypothesis for the Anderson-Darling test is that the data follow the specified distribution. Therefore, we assume that the data follow the specified distribution. Okay, p-value greater than or equal to critical value, we can assume the data follow the specified distribution. Here's another example. We have a p-value of 0.03. Our critical value is 0.05. Our p is less than our critical, therefore we reject the null hypothesis. Therefore, we cannot assume the data follow the specified distribution. P-value less than the critical, we cannot assume the data follow the specified distribution for the Anderson-Darling test. Remember, this null hypothesis and alternative hypothesis only apply to the Anderson-Darling goodness of fit test. Okay, but something I want to clarify for all of us engineers out there. Again, we're stepping away from statistics and we're talking as engineers, because the whole goal of these videos is to give you as an engineer the ability to talk with your customer and explain so that nothing comes as a surprise to you or them. So let's say you have a p-value of 0.08 and a p-value of 0.8, right? Both of those values are greater than or equal to our critical value of 0.05. In both cases, we fail to reject the null hypothesis, and therefore we assume that the data follow the specified distribution. Your customer is going to be a lot happier, and you will be a lot happier with the p-value of 0.8 as opposed to the 0.08, because even though they both pass, one of them is a much safer pass. To put it in terms that an engineer generally is more familiar with, let's talk capability. A capability of 1.34 or even 1.33 passes. But if you have a capability of 7.88, you feel really good. Chances are you're a little worried that we messed something up because that's an incredibly high capability. But you have to remember that even though it's a pass-fail test, it's a hypothesis test, as an engineer we can say it's a pass-fail test, we also feel much more comfortable with a higher p-value because that gives us much more confidence. Again, as engineers, it gives us much more confidence that the data follow the distribution. Okay? Again, we're talking as engineers here, not as statisticians. I like to specify that because mathematicians and statisticians really hate when us engineers take shortcuts. But we live in the real world with real limitations, and we have to do the best with what we have. So now we've run through a couple of examples, and you're really hearing me say specified distribution a lot. And I want to come back to this because this is incredibly important. As engineers, we really only care about normality unless we fail to assume normality. So the Anderson-Darling is not a normality test. We use it to assess normality, but it's a goodness of fit test. So the specified distribution is the distribution represented by the cumulative distribution function that is used to calculate the weighted probabilities. So if we're testing for a normal, to see if the data follow a normal distribution, we would use the normal cumulative distribution function. If we're testing for Weibull, we'd use the Weibull cumulative distribution function. Exponential, the exponential. Okay, so I want to really specify that the parameters matter. The Anderson-Darling test evaluates the goodness of fit of data to a known distribution with specified parameters. Not all tests do with specified parameters. We'll see that a little bit later. But the Anderson-Darling, the parameters matter. So if you're just throwing random parameters in and not using maximum likelihood, or even you're using maximum likelihood, but computers can only hold on to so many decimal places, you might run into some rounding things, especially when it comes to like a 3-parameter Weibull. That just gets unbelievable. A small change in your parameter can lead to a passing or failing for your specified distribution. So in the normal distribution, we think of it in terms of mean and standard deviation, but they're actually location and scale parameters. It just so happens that when you do maximum likelihood estimation on the normal distribution, the location and scale parameters are equivalent to the mean and standard deviation. Now, maybe in a later video we can tackle that because it's a really, really cool concept that because it's the mean and standard deviation, we call them the mean and standard deviation for mu and sigma when they're actually a location and scale parameter. But again, if you don't use the right parameters, you'll get a different result. Okay? So there we go. Let's get into some actual math here. So calculating the Anderson-Darling test statistic. I have all of the equations up here, and what we're going to start doing is I'm just going to kind of talk you through them, kind of tell you what each of these variables is, and we're going to start to break them down and try to simplify them as much as possible, because later in this video, we are going to actually go into a spreadsheet software, and we are going to do this by hand. So to calculate the Anderson-Darling test statistic, AD equals minus n. N is the number of samples, minus 1 over n times the sum of all of this stuff to the right. So the sum of 2i minus 1 times, then in these brackets here, the natural log of f of y. Yi is the ith ordered data. F is the cumulative distribution function for the specified distribution using the parameters. And natural log is just the natural log of that. Okay? Plus the natural log of 1 minus the cumulative distribution function of y, of the ith reverse ordered. it'll make a little more sense in a second. But y of n plus 1 minus I is the ith index, the ith value, if you were to flip them in descending order. yi in ascending, y of n plus 1 minus I descending. Okay, so let's simplify that down. We'll say the Anderson-Darling test statistic equals minus n minus beta. Beta equals 1 over n times the sum of that whole mess. Let's simplify it further. So we're going to break this down a little bit, and we're going to throw the 1 over n inside of our summation. That way we can pull out C1 of 2i minus 1 over n. We're going to take this natural log of the cumulative distribution function of yi and call it C2. We'll do the same of the 1 minus, and we'll call that C3. So what we can do then is replace those in there, and we can say that beta equals the sum from I to n of C1 times C2 plus C3. Again, we have everything listed, where n is the number of samples, f of x is the cumulative distribution function, y of I is the ith sample in ascending order, and y of n plus 1 minus I is the I sample in descending order. So here is our equations for the Anderson-Darling test statistic, all broken down. The reason we broke them down this way is once we get into the spreadsheet software, each of these, C1, C2, C3, we're going to have be a separate column just to make it that much easier when it comes to calculating for each individual data point. So once we have our Anderson-Darling test statistic, we can use that to calculate the p-value. We can take our piecewise function, where p equals each of these lines is a different function based on what the AD star value is. So AD star is our modified Anderson-Darling test statistic. We calculate that using the equation on the bottom here. This one right down here. AD star equals the Anderson-Darling test statistic times 1 plus 0.75 over n plus 2.25 over n squared. Again, n is the number of samples. Okay, so let's go back up. We have our AD star. Now we can plug this into the piecewise function. So if the AD star is greater than or equal to 0.6, we use that top function, plugging in the AD star in each of those sections. If the AD star is greater than or equal to 0.34, but less than 0.06, then we use the second function here, again replacing our value for AD. If we have a value of AD star that is greater than 0.2 but less than 0.34, we use this equation. Now, I'm not going to read these all out because it's just a lot of constants and exponents. So again, AD star less than or equal to 0.2, we use the last function. Okay, so that's how we would calculate the p-value. And then we would use the output of this function to compare with our critical value and determine whether or not we reject the null hypothesis or fail to reject. Again, speaking as an engineer, whether we can assume the data follow the specified distribution or we cannot assume. All right, are you ready? Let's perform this test by hand. So now we're going to perform the Anderson-Darling test by hand in a spreadsheet software. If you want, there's a link in the description below that will take you directly to and open up the workbook that we are going to be making here. In that workbook, it's going to open up this video and you can follow along right in the workbook. Or you can download the Excel workbook and do it in Excel. It's totally up to you. I'm going to do it in our wonderful software, ENG Sheets. All right, so now it is loading here. And it's going to ask me to sign in. I'm already signed in because this is my work computer, and I've been successfully signed in. So if you're already signed in, it should automatically take care of that for you. If you are not signed in, you'll have to sign in. It goes through Microsoft, and then Microsoft just lets me know who you are. That way I can determine if you have access to QE Suite. If you do not, you will automatically be given a 2-month free trial, in which time you can use this to your heart's content, and I really encourage you to because it is wonderful software. All right, so here we are. And as I mentioned, let's say you just go to engsuite.org/engsheets/web. If you click this learn and then click on the Anderson-Darling, that will load this workbook and a little task pane will pop open over here with this video for you to follow along. We'll go back to the home. All right, so the first thing that we're going to need to do is get our data here. The data is in the description, so go ahead and copy that, and then you can just paste it right in. Okay, so next thing we're going to do, and I better pull up my notes because we have a lot to type. Okay, here we are, and I'm ready to go. And what we're first going to do is in this column here, C1, we're going to type in AD test statistic. And we go all the way over to I, and we're going to merge that. Okay, so our first column is just going to be I. Our second is going to be Y. Then we're going to have C1, C2, Y, and minus I, I, and C3, C3, and S. Okay, awesome. So here, we'll just type in 1, and then we are going to just drag down, not control. We'll drag down, and that automatically increments our values. Look at that. And we're going to have to go one more because we started one column down. Okay, so Y of I here, maybe I'll just do sort, and then we're going to select our numbers, close our parentheses, and look at that. Our data is sorted in ascending order. Pretty cool. All right, so before we go on to C1, what we're going to have to do is we're going to have to fill out some descriptive statistics here. So the first thing we're going to do is get the average, the mean of our data. Come over here. Then we're going to have to get the standard deviation, so stdev.s. Again, make sure you get all of the data here. And then we're going to need a count. So we're going to use the count function. Again, make sure you get all of your data. Okay, awesome. Now we can move back here into the C1 column. So we'll do equals, and this is going to be, let's see here, 2 times I, and then minus 1 divided by N. So we're going to come over here and we'll have to put some dollar signs in front of both the Q, well, just the 4 really. I like to put it in both. There we go. And then if we double click on that, it automatically drags it all the way down for us. Pretty sweet. Okay, time to do C2. So C2 equals natural log of norm.dist. And then we take our x value. So in this case, C2 is norm.dist of yi. So we're going to take yi, which is right there. And then we're going to take our mean and then our standard deviation. And then we're going to make sure we type in true to get the cumulative distribution function. And oops, I forgot a parentheses. And there we go. And now what we're going to want to do is we're going to want to make sure that we make these absolute cell references for both of those. Then we'll hit enter and double click to drag all the way down. And look at that. Automatically fills out all of our data. Okay. Now we want to do y of n minus I. So this is just sorted in descending order. So we're going to do sort. We're going to select our numbers here. And we don't care about sort index here, -1. And again, you might notice these functions all take the same format as Excel. That is on purpose. That way you don't have to learn any new syntax. There we go. Sorted in descending order. Now for C3, that is going to be the natural log of 1 minus norm.dist of y of n minus I, or technically n plus 1 minus I, and then our mean and our standard deviation. And we can close, not yet, sorry, we need to add true, and then go ahead and close that up. And what we might want to do right now while we're in here is make these absolute cell references and enter. Double click to autofill, and then now we're going to start doing everything inside of the sum. So this is we called this one S. So this is C1 times C2 plus C3 in parentheses. So we take C1 times parentheses C2 plus C3. And we hit enter, double click to autofill all the way down. Awesome. So now we have the innards of our entire Anderson-Darling test statistic. All we got to do is put together our weighted values for each of these. So we're going to go into the cell 09, and we're going to call this one, we'll call it tutorial, because then we'll run it with the QE Suite function just to see how fast and easy it is compared to doing it by hand, because it is really cool, and also to validate to make sure that we're getting the right results. We'll call that AD and P. Okay, so in here, our Anderson-Darling test statistic is minus n, so minus n, minus the sum of all of these values. So if we take the sum of all of those, we get an Anderson-Darling test statistic of 0.537685516 ... That doesn't really mean anything to us because we don't have a critical value for our Anderson-Darling test statistic. So that means we're going to have to take and turn that into a p-value that we can then compare with our critical value. So in K1, we're going to type in p-value, and we are going to merge. So the first thing that we need to do to calculate our p-value is we're going to need the modified Anderson-Darling. Now, if you remember, that equation is going to be our Anderson-Darling test statistic times 1 plus 0.75 divided by n plus 2.25 divided by, we'll use the power function, n squared. All right, and there we go. There is our Anderson-Darling modified test statistic. So now we're going to use our piecewise function to actually turn that into a p-value. So I'll just call this column condition, and I'll call this one p-value. Okay, so our first condition, let me flip my page of notes here, is that the modified Anderson-Darling is greater than or equal to 0.6. So what we're going to do here is we're really just going to calculate each of the p-values individually, and then over here we'll use some if statements to make sure that we are doing the logic here. But we'll just calculate them individually over here for now. Okay, so if the modified Anderson-Darling is greater than or equal to 0.6, our p-value equals exp of 1.2937 minus 5.709 times the Anderson-Darling modified plus 0.0186 times, we'll use the power function, of AD star squared. All right, looking good. We'll close up those parentheses. Now, we have another condition. If the Anderson-Darling test statistic modified, the AD star, is greater than or equal to 0.34 or less than 0.6, then our p-value equals exp of 0.9177 minus 4.279 times our AD star minus 1.38 times our AD star squared. All right, close up those parentheses there, enter. All right, our next condition is if 2 is less than AD star or is less than 0.34, and I need to put a 0.2. So if AD star is between 0.2 or 0.34 exclusive, then our p-value is 1 minus exp. That 1 minus is so that we can adjust these p-values so that as the Anderson-Darling test statistic gets lower and lower, our p-value gets higher and higher. So 8.318 plus 42.796 times AD star, and then minus 59.938 times power again of AD star squared. Enter. There we go. Look, it's getting real high here. As we know, if the p-value were lower, if the Anderson-Darling test were lower, the p-value should be greater. But again, none of these are telling us anything yet until we use the logic. So our last condition is if AD star is less than or equal to 0.2, then, again, 1 minus exp of 13.436 plus 101.14 AD star again times, don't forget the times sign, and minus 223.73 times power, we got to square it again, 2, and close our parentheses. There we go. So we have our p-values if each of these conditions were met, and now we need to add in some logic here. Equals, and we're going to say if AD star is greater than or equal to 0.6, then our value, if true, is going to be that value. So we're going to kind of work our way in one direction here. If that's false, we're going to do another if statement. And in this case, what we're going to want to do for our logical test is say if AD star is greater than or equal to 0.34, then our value is going to be this condition. Else, we'll do another if statement, and we'll say if AD star is greater than 0.2, we'll do this condition. Else, if, actually, we don't need to, because if it fails all of these, then we know that it's less than or equal to 0.2, so then we can just return that, and then we close our last one, then our second one, and our first one. Enter. There we go. There's our p-value. So let's use QE Suite, and we'll do QE.Anderson-Darling, and we're going to go in here and collect our data, and we could hit it, just close it up right now and hit enter, but I'm going to add this, and we'll hide our graph. There we go. Both of those match up. We did it. All by ourselves, we have now calculated the Anderson-Darling test statistic and the p-value for this data against the normal distribution. All right, that is a lot of work. It was so much easier just to use the QE Suite function, but now we know how it works. Now we know how QE Suite, Minitab, and any other software would calculate the Anderson-Darling test statistic for the normal distribution. Now, maybe later when we're doing some maximum likelihood, we'll talk about maybe how to use this with other distributions. Again, what you would really be doing is in like your C2 or C3, instead of using a norm.dist, you'd use maybe a Weibull.dist like in Excel. However, for today, since we're only talking about normality, we use this. Okay, but let's actually use these values to talk about this distribution. So the Anderson-Darling test statistic, we return it because it can be nice to know. It's cool to see, but really what we care about is this p-value here. So in this case, our p-value is 0.15. Our critical is 0.05. So our p-value is greater than or equal to our critical. Therefore, we fail to reject the null hypothesis. Because we used the Anderson-Darling goodness of fit test for a normal distribution with the specified location and scale of mean and standard deviation, we can assume that the data follow the normal distribution with mean and standard deviation as the parameters. So if we were to run a capability analysis on this data, that capability would be considered reliable because we can assume normality. So that's pretty much it. Let's jump back into the PowerPoint for a little bit of a conclusion here. So just to conclude, the Anderson-Darling test can be used to evaluate goodness of fit of a data set to a specified distribution with known parameters. Doesn't just have to be the normal distribution. It's usually one of the first that we use in engineering because it's more selective than other normality and goodness of fit tests, which makes it an excellent choice to start. But you have to make sure you check with your organization for your critical value when comparing with the p-value. Most organizations will use a 0.05, but different organizations have different requirements. So make sure you know what your organization uses and have fun with it. You know, it's a really cool thing to know how the math works and how we did it. So I highly recommend going and actually doing the math yourself, typing it out, and you can always download the Excel workbook below or click that link and go directly to the one in ENG Sheets. Thank you so much for watching. Have a great day and please do something awesome.